Okay, let's take a look at counters. 12. Look at this stuff. So first thing, we have two types of counters. What we call ripple counters. So ripple counters are counters where these are the cheaper counters. These are basically where the count ripples down through the counters, the counts or the JK flip-flops. So at the end of the last lecture, I'll let y'all see a basic counter. And the counters that we're going to be dealing with here is going to be a binary counter, which is a 4-bit binary counter. So a 4-bit binary counter can count from 0 up to 15. And then what we do is we're not going to draw the JK input. We know that if we connect the JK inputs to a 1, then every time I come up here and pulse the clock, the thing will do what? It'll toggle, right? Okay. So what we do is I take the Q of this one, and then I'll feed it into the clock of the next one. And then I'll take the Q of this one and feed it into the clock of the next one. And then I'll take the Q of this one and feed it into the clock of the next one. So what happens is if we start off here, and unfortunately guys, we draw circuits from left to right, but this guy right here would actually be the A output. This would be the B output. This would be the C output. And then this Q right here would be the D output. So anytime we look at a data sheet and we see A, B, C, D, those are weighted binary numbers, with A being the least significant bit and D being the most significant bit. So if I was to write this down, then it would go A, B, C, D, right? You understand that? This would be the way. But when we draw them from left to right. So it makes my count here look like it's opposite of what it is. So I come over here and I put, and this is edge triggered on the rising edge, right? And let's just start off with all these equal to 0. And then what would happen is I would come over here and, no, these need to be low active, sorry. Like a 7476. So I'd come over here and we start off doing this, and on the low going edge, this right here would go to a 1. Now nothing would happen here because it's looking for a low going edge, right? You understand that? Okay. And then on my next pulse, so that'd be a 1. Then I'll do this, right? And this will go to a 0, right? You understand? So it will like this, so the output of this one would go to a 1. So if I was to start off, I started off with this, then I had this, now I've got this. And then I would put another clock pulse, I'm going to have to go down here, guys. Okay. So rising edge, nothing happens. Falling edge, this right here would go back to a 1. Nothing happens over here because it's looking for a wall. It's looking for a falling edge, right? You understand? So now we got this guy right here. Then I go like this again on the falling edge. This right here would go to a 0. This one sees a falling edge. This right here would go to a 0, right? This one sees a falling edge. This right here would go to a 1. So now we get a count of 4, and we can keep going, right? You understand? So these are counters. JK flip-flops are counters, but notice the count is rippling through. So these are what we refer to as ripple counters. Now the propagation delay, and what is the propagation delay? What is the propagation delay? the time it takes the output to respond to the change in an input, right? You understand that? So what would set the propagation delay of this guy would be this guy way out here. Because it's got to propagate all the way through all those other flip-flops before it ever changes. So if my count changes faster than this guy over here can change, then the counter's going to lose count. So if this guy right here had a 40 nanosecond count, and this guy here had a 40 nanosecond count, and this had, I'm propagation delay, this had a 40 nanosecond, and this had 40, then my propagation delay would be 160 nanoseconds for the counter to count. Count all the way up to 15. Y'all understand that? So the first ones would work fine, but after a while it would lose count if I was trying to make this count, if I was trying to make these things count too fast. So these are called ripple counters. That means the count has to ripple through all the other JK flip-flops inside there. A synchronous counter, we're going to time these all at the same time. So we'll have to look at that. So ripple counter, these are also referred to as asynchronous counters. And here, I don't know what's going on here. Let's see this. So this is showing us our outputs. So I guess this is figure 12-10 in your book. And what we've lost is we've lost this over here. So most counters have a reset on them, a reset to 0. So when we use the term reset, that means Q goes to 0, right? So you can understand every counter I've ever seen always has a reset to 0 because you have to count. When you count, you need to start counting from what? 0. So before we started using this, of course, we would pulse this low and then bring it back high, and then all my Q outputs would do what? Go to 0. Right? These are 74, 76s. That was what we played around with at the last. So what would happen is reset. We reset it. So before we use a counter, what are we probably going to do? What? We're going to reset it first, right? Everybody make sense? So we start off with all the outputs equal to 0. And this is my least significant bit. And this right here would be my most significant bit. So what would happen on the first going edge? Well, it would toggle, right? You understand. This output would go to a 1. This one right here would still be a what? 0, 0. So that would be a count of 3. Right? On this low going edge, this guy right here would toggle to a what? To a 0. This one would go to a what? A 1, which would be a count of 2, right? On this low going edge, this one would go to a 1. This would be a 1 because it didn't see a low going edge, and this right here is still a 0. So this would be a count of 3. On the next low going edge, this one's going to toggle, right? You understand? So it's going to toggle from a 1 to a what? A 0, right? All right, this guy's going to toggle from a 1 to a 0. This guy's going to toggle to a 1, which would be a count of 4. Everybody okay? Yes or no? On the next low going edge, this guy's going to toggle. This guy's not going to toggle because it didn't see a 0, right? This guy's not going to toggle, which would be a count of 5. On the next one, this guy's going to toggle. So this guy is toggling every time, right? You understand? The next one toggles depending on the Q output of its previous predecessor. So right here, this one goes to a 0. Well, if this one goes to a 0, this one's going to toggle because it saw a low going edge. This one hadn't saw a low going edge, so it would stay to a 1, so this gives us a count of 6. On the next low going edge, this guy right here is going to toggle. This guy here is not going to toggle because when this goes to 0, this one toggles. When this one goes to 0, this one toggles, right? You understand? So this is going to stay there. This is going to be a count of 7. When this comes, this is going to go to a 0. This one toggles. This is going to go to a 0. This one toggles. It goes to a 0, and this thing just rolls around. And now it's ready to start counting again, right? You understand? Now, another thing we need to look at, so one popular application of a counter is to divide frequency. By the way, the total number of counts, including zero, so we start counting from zero, is called the counter's modulus, including zero. So this would be a modulus what? So this would count from 0 to 7. So what would be the modulus of this count? Huh? 8. Thank you. 8. 0, it starts from 0. 0 is one of your counts, right? So a lot of people think we count from 1, but we don't count 1. That's the first thing we say. We're actually counting from what? 0. It's just that we usually don't say 0, 1, 2, 3. Usually when we start counting, we say 1 because we understand that we're counting from 1. So the modulus of this counter would be a modulus 8 counter. Now look at the frequencies of the output. So notice for every 2 pulses of our clock, for every 2 cycles of our clock, I get 1 cycle out. So if this guy right here, if this clock was running at 10 kilohertz, then what would be the frequency of the 2-0 output? So for every 2 of my input pulse, every 2 cycles of my input, let me do this with a different color besides black so it shows up. Be 5 kilohertz, right? Okay. So here's 2 cycles of my input. We're looking at low going edges, right? Okay, so rising, that's the low going edges. Speeds are to see from right here. Low, right, to low. Okay, so here I have 2, down here I have what? 1, right? You understand? Now look, this one will start from here. No, I'm sorry, we'll start from here, this rising edge here, to this rising edge here. So 1, 2, 3, 4. So every 4 cycles up here, I get 1 cycle down here. So this gives me a divide by 2. This gives me a what? A divide by 4. And the next one is going to give me a divide by 8. So I'm putting in what? So what would be the output frequency right here? So we already said this is going to be 5 kilohertz, right? This one right here would be what? 2.5 kilohertz. And this one right here would be what? Yeah, that's an 8. It goes by binary. So we go 2, 4, what? 8. What would, if I added another one, it would be 16, 32. So we could get just, and we'll show you how we can set the modulus of the counter. So you could take this guy and divide it by 2, or you could take that guy and divide it by 8, and you'll get the same number. So we use these guys as frequency dividers. So I wanted to, Alabama Power 60 hertz is a lot more accurate than the voltage that Alabama Power puts out, because the 60 hertz is so important because it's something referred to as impedance. And if you had AC, you understand that. So the impedance of a circuit is determined by frequency. So if they used 100 cycles, all the transformers wouldn't pass the way they wanted to. If they use something lower, the transformers will pull more current and they become more inefficient, right? You understand? So 60 hertz for Alabama Power is very, very important. So we went up there and we went up to the we had one of our students that was working in the main Alabama Power building up in Birmingham, and they took me down to, I think it was like the 5th subfloor under there. And that's where their control center was. That's where their computers are that runs the whole power grid in the state of Alabama. One of their computers. I think they have 2 for obvious reasons. Because if something happened to the one downtown, they needed to have another computer that's backed up, right, that's in another location. Banks that have their own processing center, and that's what I worked on for a while, every day after they ran all their checks and everything, they had to take a backup copy, so they had to have removable storage, and they had to take that to an off-site location. Because why? Because their bank could catch on fire or a tornado could come through, and they lose everything they know, which is bad, right? So if a bank don't know how much it's worth, that's very, very scary, right? So what we wanted to do was make a digital clock. Well, the problem is this is 60 cycles per second, and I needed what? I needed 1 cycle per second. So I just figured out how to use counters just to get a divide by 60. And it wasn't bad. So I came in the same circuit that we hooked up before, where I came in with this little circuit right here. You remember this guy? First lab, wasn't it? Or second lab. So I brought Alabama Power in right here at 60 cycles per second, but this is analog. I ran it through this switch and converted it to digital. I ran this into my counters, and I used to have the circuit hooked up, counting in seconds. And like I said, these computers right here, the I/O bus runs at 166 megahertz, but it's got to be in time with the high frequency bus, right? You understand that? So how do they make it in time? Well, they just take, and they don't use 2 different clocks. They just take the clock that the processor's running at and divide it by something to get a 166. And that's why all your frequencies are weird, like 1.1, 2.1 gigahertz, right? You understand? If you actually looked at the true frequency, you would see it would be a multiple of 166. So they just take that high frequency and just divide it down. So we can use counters we can use them as counters, or we can use them as frequency dividers. But what's the modulus of a counter? This is going to be on the test, huh? It's how many counts we allow it to count, right? You understand that? So here we're counting from 0 to 7. So the modulus of this counter would be a modulus 8. An octal counter, right? Normally we don't see octal counters. Basically the 2 main categories of counters we have are BCD counters and what we call binary counters. A binary counter, you let it run to its maximum modulus. A BCD counter, we only let it count from 0 to 9. So these are the 2 categories of counters. I could make a modulus 8, and we'll show y'all it's not hard, out of this guy right here. So binary counters, we can set the modulus of the counter. In fact, that's what they've done with the BCD counter. They set the modulus of the counter. Let me bring in a blank sheet. And I'm not going to draw the JK. The JK is held high, right? So I'm going to bring my count in here. I carried away. So this guy would have a modulus of 16. Good. We have a modulus of 16. But it's a ripple counter, so it's still got a ripple down through there, right? What if I took this one? So what I'm going to do is I'm going to connect all the clears together. That's a clear guy that's supposed to touch. And I bring this into a NAND gate. Oops, let me go the other way. Now since I'm using the same color, usually we don't loop, but I want to. So what would the modulus of this guy get? So I'm looking at this guy right here. So as soon as this goes to a 1, and soon as this goes to a 1, we're going to reset the count. And you won't even see this. So we start off counting. Start off at 0, right? Then we go to 1. Nothing's going to happen, right? You understand? This will be a 1, but this one right here would be a what? A 0. So this is going to stay at a what? A high. That'd be a 2. Now this is a 0 and this is a 1. I'm sorry, this is a 0, this is 8, right? So what we're doing is we're looking at this guy right here and we're looking at that guy right there, right? Everybody okay? Right. Yeah, so this is going back to A. Oh, I'm sorry, wrong. This is, that's right. It's just what you got to get used to is when we draw circuits, we draw them inputs on the left, outputs on the right. Well, this is A. A is the least significant bit. So when I come up here and look at my count, this is A, this is B, this is C, and this is D. But it's drawn backwards because over here we draw inputs on the left and outputs on the right. So that's why I've got A, B, C, D up here. Actually, when we look at counters, they're going to call this QA, they're going to call this QB, they're going to call this QC, QD. That's the way they label them because they're the Q output of the counter, right? You understand that? So what we're looking at is we're looking at the output of B and we're looking at the output of D. When these two right here go high, as soon as these goes high, we're going to reset the counter. So are those two high right now? No. So that'd be a 2. The next count would be a 3. It's not going to reset. The next count will be a 4. It's not going to reset. The next count will be a 5. It's not going to reset. The next count will be a 6. It's not going to reset. The next count will be a 7. It's not going to reset, right? You understand? The next count will be an 8. It's not going to reset. The next count would be a 9. It's not going to reset. The next count will be this, but we never see that because what happens? It resets instantly. So we never ever see an 8 because we reset on an 8. So what would happen is this guy right here would roll back around to what? 0. And then it would start counting again. So what type of counter is this? It's counting from 0 through 9. What type of counter is it? Huh? Yeah, this is a BCD counter. So if I look at the circuit of a BCD counter, all they do is exactly what they do here. I could convert any binary counter into a BCD counter just by resetting it on what? On 10. We're actually resetting it on 10, right? You understand? So as soon as it goes 10, the output goes 0 and we'd never see it. And then of course all we have to do now is a figure out another way we can reset it. So I could set this thing up. I could have any modulus I want to. I could reset on a 4, and then it would be a modulus 3, right? You understand? I could reset on a 5, and then it would be a modulus 5, right? You understand that? I could reset on a 5, it would be a modulus 5. So using AND gates or NAND gates, whatever's required on the clear, I can establish any modulus or any division ratio I want to. So instead of me buying this thing and building it, you know, I'll buy it. And so we'll look at a 7490, which is a BCD counter, and its cousin is a 7493, which is a binary counter. And it's going to be 4-bit. So the two main categories of counters are BCD. Why? Because that's what we understand. I could take the output of a BCD counter and hook it up directly to 7447, which is it's a 4 to 7 segment decoder, right? You understand that? And I could have a counter. I mean, and I would be seeing decimal instead of binary. So all these guys are just JK flip-flops. That's all they are. And some of the things I could do with the JK flip-flops is I can add presets and clears, and we can do a lot of cool stuff with these guys. So we're going to see JK flip-flops a lot, but all I have to understand is I'll come over here. Everybody okay? And I'll see this. I'll see an IC. It's going to be called a 74 something 93. And it's a binary counter. So I know a binary counter, we're going to let it count in binary, right? You understand? I can come over here, and now what makes it up? Well, really, I know now it's just all counters use JK flip-flops. They use that, but that's nice to know stuff, right? You understand? All I know is a counter does what? Counts. How does it do it? Well, I don't care, right? You understand? I don't really care the internal circuitry, so we're getting into the combinational logic circuits now that's very complicated. Because if you go back and look at what makes up a JK flip-flop, good gracious, guys, there's a lot of ands, and y'all understand that. Then what makes that up? How many transistors that makes it up? And I told y'all about the milling machine I worked at Beaches. That sucker was all transistors. And they could have probably built that whole thing on one little circuit card, right? You understand, using integrated circuits. But this was before integrated circuits when that thing came out. But they was already doing that, right? You understand that, which is pretty neat. Are we okay? And so what would be the modulus of this guy? Here we got a reset on here, and what's the reset? How they tie the reset in and how they tie the feedback in to set the modulus on the counter, that's really no concern with us. All we know if it's a modulus, all we need to know if it's a modulus 10, right? You understand, or BCD, or a modulus 16, which would be a binary count, if it's a 4-bit count. So these are ripple counters, and this is why they're called ripple counters, because the count has to do what? Has to ripple through all the JK flip-flops. So these guys are less expensive, but the problem is how fast they count would be limited, because how far it counts is not set by this guy, it's set by this guy right here, right? Because it's got to ripple all over there. So if these guys don't have time to ripple all the way through, then a ripple counter can lose counts. So one of the things you're going to look at on your data sheets is how fast can these things count. Divide by n, so this is called the modulus. So if we divide by 5, which means we'll reset on 6, right? You understand? So if the modulus, we reset on 1 plus what we want to set the modulus for. Any modulus counters can be formed by using external gate. And usually we use AND gates or NAND gates depending on what's required to reset the counter. So here, so all we're doing is resetting on a what? So we're looking at this input, which is A input, the output. This is the B, this is the C. So this is, if we look at data sheets, they're going to call this QA, they're going to call this QB, and they're going to call this QC. Which one's the most significant bit? C is the most, A is the least. So what we're doing is we're looking at C. So if C goes to a 1 and A goes to a 1, we're going to reset this thing. So we start off counting here. That'd be 0. This would be 1. This will be 2. This will be 3. This will be 4. This would be 5. We'll never see 5. It's going to do what? It's going to reset. So this would be a modulus 5. So it would divide by 5. Now the problem is when we set these weird, if it's not a power of 2, like a divide by 2, a divide by 4, a divide by 8, divide by 16, then our output, so notice this would be what we call a 50% duty cycle. Now what's the duty cycle of a digital waveform? Huh? The duty cycle.
Like if it's one wavelength to whatever the cycle is, right?
You got it right in your head, but the way you're saying it. So what we have is, I come over here, and the time it takes for one cycle is what we call the period. Now you notice on this guy, the size of the amount of time it's setting at a high and the amount of time it's setting at a low is equal to each other. So we would say this guy right here has a 50% duty cycle. So the duty cycle is the percent of the period that the waveform is high. So if I came over here and did this, the frequency would be the same. The frequency would be the same because the rising, if we're going from rising edge to rising edge, it's the same amount of time. But what is varied is the what? The duty cycle. And this would probably be around what? Maybe around 75%. I'm just guessing at it. We'd have to actually measure it. That makes sense. And then, of course, if I was to come over here and do this, then we'll go here, same time, and we'll drop down to here and go over there. Then my duty cycle here might be 10%. Now, this is important because the average DC that we get out of this thing. So which one would give us the most? A duty cycle of 75%, a duty cycle of 50%, or a duty cycle of 10%? Which would be the highest average DC out of this? Okay, so let's look at this. So this would be a duty cycle of 100%. So this is 12 volts. Here's 0, sorry. And I can't figure out what's going on there. So if this is 12 volts, and this right here this is my 0 reference, and I put my meter across that, I would measure 12 volts. This is a duty cycle of 100% because it's a high 100% of the time. We have no pulse anymore. When it's sitting down here, this would be a duty cycle of 0% because we get no voltage out. So just looking at that, which one of these would give me the highest average, 75% or 10%? 75%, right? Don't it make sense? The formula is DC, and this is average, is equal to, would be equal to DC max times the duty cycle. And that's the fraction. It's not this, so this would be 0.75. Now, why is this important? This is the method, preferred method that we use now to control the speed of a DC motor. This is called pulse width modulation. You can research this, PWM. This is the way we digitally control DC motors. Used to, we'd actually give it a different DC level. So we're using these big things called SCRs and transistors and stuff like that. But the problem is that digital consumes less power than analog because it's either fully on or it's fully off. So if it's fully on, my control device is not dropping any voltage. If it's fully off, it's conducting no current. So what we can do is, and now you have to understand, digital devices or solid state devices can never actually drop 0 volts. But what we can do now is we can control motors with very small, with a lot smaller electronic devices. And that motor don't care because the motor don't run off, the motor runs off an average, right? You understand that? So I can show you this. I can control the speed of a DC motor very precisely with pulse width modulation. But what happens if I do this? Let's look at the duty cycle here. So this is 1, 2. This is 1, 2. This is 1, 2, 3. So I'm not having a 50% duty cycle anymore. So anytime you come up with a modulus that's not a multiple of a power of 2, 4, 8, 16, then you're going to end up with duty cycles that are not 50%. So look at this one. Here it's high 1, and then it's low. What? 1, 2, 3, 4. So this guy right here would be this right here would be a 25% duty cycle, right? No, it'd be a 20% duty cycle because we have 5 pulses and it's high 1, right, out of 5. So it'd be a 20% duty cycle. This right here, we have 1, 2, 3, 4, 5 pulses, and this would be 2 2/5. It'd be a 2/5 duty cycle, whatever that is. Huh? Yeah. And these are still called. So what I can do by using outside gating is I can set the modulus of the counter. So we can get any modulus we want. If I needed to divide by 6, then I would reset on 7, right? Does that make sense? And so now this is what we did. If I took a divide by 10 and fed it into a divide by 6, then I would get a divide by 60. And this is they don't show it here. It's in the lab. Oops, let's make this guy right.
What the little sign mean again? Inside that bird.
This means it's what we call a Schmidt. I think it's 2 T's. We'll look one of these things up. The problem we have with a standard TTL gauge without the symbol in it, this guy right here can recognize anything of around 2 volts as a legal high, and it represents around 800 millivolts as a legal low. Now this guy right here usually guarantees around 2.4 volts as a legal high. We've talked about this several times, right? And it guarantees around 400 millivolts as a legal low. So we built into these things, we have a 400 millivolt safety margin between what we assume, what the outputs guarantee, and what the inputs will accept. So this is why, we don't, so when we look at legal levels, we look at the outputs. We don't look at the inputs, because if your outputs are legal, your inputs are bound to be legal, right? You understand? So this is why we say normally we assume a legal high is 2.4 volts and a legal low. Well, what's between 800 and 200 millivolts? I'm sorry. Why do we consider that region invalid? Why? Because we don't know where it's supposed to switch. We just know it's going to switch somewhere in that range. Somewhere in there it's going to switch. Odds are it's going to switch before it gets up to 2, because 2 is the minimum value. So the problem is that I can have 2 of these guys side by side, and they're not going to switch at exactly the same voltage level, right? You understand that? They are not going to switch at the same voltage level. Schmidt triggers have no invalid range. So they call it a threshold voltage. So let's say the threshold voltage on this guy is 2 volts. The threshold is 2 volts, and the threshold is 800 millivolts. Then what would happen is I can come over here and I can put this all over the input, and if this right here is 2 volts, it would accept it a high. But once it's accepted as a high, this right here means nothing. It's looking for this to drop below what? 800 millivolts. And that's why it's drawn with a hysteresis, because it's not going to switch at the same spot. So a Schmidt trigger has no invalid state. So that means if I come over here and close this switch right here, this capacitor starts charging, and when this thing gets up to the threshold, the output's going to reset, right? You understand? And we'll look at this. So we see this a lot inside devices that gives us an automatic reset every time we power this thing up. We'll see this a lot. And this is shown in the lab, but you have to use basically a Schmidt trigger, because this guy over here might reset at a different time than the one right beside it, right? You understand that? So Schmidt trigger inputs. These are inputs. What advantage does that have over standard TTL inputs? It has no what? Invalid state. Has no invalid states. There's no such thing as an invalid on a Schmidt trigger. When it gets up to a certain level, it will switch. It will recognize it as a high, and it will not recognize it as a low until it drops down below the wall. The low. Yeah. So right here, as soon as it exceeds 12, as soon as it exceeds the upper threshold, it's going to accept it as a high. What about in here? Well, if this was a standard gate, I don't know, because it would be between, we don't know where it's going to switch, right? But a Schmidt trigger will not switch until what? Yeah, hits the lower threshold. And now it'll accept it as a low. So the advantage of a Schmidt trigger, we use this a lot on stuff that we're getting from the outside world, because there's so much noise in the outside world, right? You understand? That might generate a pulse that would get it into the illegal level. So these are just setting the what would be the modulus of this guy? Not quite. We're resetting it on, looks like we're resetting it on a 12. A, B, C, D. Oh, I'm sorry. No wonder you're having problems. So what they're doing is they're bringing the D, they're bringing Q3, which y'all can't see. They're bringing Q3 down, so this is Q3, and they're bringing QD, and they're bringing QC down. So QD, so they're resetting it on these two, right? So what are we resetting on? D. So we're looking for D to be a 1. We're looking for this guy right here. We're looking for D. We're looking for C. And of course, these don't make any difference because we're going to reset. But as soon as it hits that, which is a 12, this guy's going to reset on a 12, right? You understand? So what would be the modulus? Whatever you reset on is the modulus of the counter. No, whatever you to clear it, to set the modulus, you reset it on 1 plus what you want the modulus to be. Right? You understand? I'm sorry, you reset it on 1 plus the count you want it to go to. So I said that wrong.
Okay, so if we reset at 12, we will set the counter at 13, or we'll set the counter at 12.
I don't know what you mean.
So
we're starting from 0, and we're going to count all the way up, and as soon as it tries to see this, it's going to reset back to this. Okay. So what we want is we want a count. We're going to get a count of 11. That's the highest we want to count to. So we're going to reset it on 12. 12 because including 0, right? You understand? So we set the modulus of the counter by resetting on what we want the modulus to be.
But when that make it, so the counter should be at 13 then, right? At 13, set the modulus to 12.
No, we reset, whatever you reset it on is the modulus of the counter. If I want a modulus 12, I'm going to reset it on 12. But it will count from 0 to 11. So if I wanted a BCD counter, it's going to count from 0 to 9. I'm going to reset it on 10. Right? Y'all understand? And so my output would give me a divide by 10, right? You understand if I use the last one. So the modulus of the counter is how many counts you get, including what? 0. So we're resetting on 12, right? You understand? So the modulus of this counter is 12. And if I use the D output, it would divide by 12. So the modulus of the counter gives you what you get out of this guy right here. That would be the frequency we'd get out. But you got to understand your count is going to be one less, the maximum count is going to be one less than the modulus. So a modulus of 12 is going to count from 0 to 11. But if I use the D output, I would get a divide by 12. That would be my output frequency. So the modulus of the counter gives you the division ratio if you use the last thing that you let the count count to. So 7493. Y'all got, oh, y'all don't have y'all's computer out. I'm gonna bring up the data sheet on 7493. So what's the difference between the 54 series and the 7400 series? We talked about this. The 5400 series is what we call military grade. It has a higher specifications. It has better specifications. So if you looked at the standard TTL voltage limitations on your VCC is 5 volts plus or minus 25%. So it means if you get below if you get above 5.25 or you get below 4.75, your outputs are no longer guaranteed. Military grade is 5 volts plus or minus 10%. So it has a wider range. So military grade has better specifications. They cost more money, right? You understand that? The 7400 series is what we call commercial grade. This is the one that we're using. So it says this right here is a 7490, 7492, and a 74 LS 193. So we have what we call a decade. So decade means it's a BCD counter. It's going to be able to count from 0 to 9. We're going to reset it on 10, right? You understand that? A binary counter is going to count from, if it's a 4-bit binary counter, it's going to count from 0 to 15, right? It's going to give us, because it's not going to reset because you got 4 bits. If you got 4 bits, it's going to count from 0 to 15, right? You understand? If I want a modulus less than 16, that's where we're going to reset it on something. Each of these monolithic, what does monolithic mean? It means these things are made on one wafer, one little old chip inside there. Counters contains 4 master-slave JK flip-flops and additional gating to provide a divide by 2 counter and a divide by 3 and 3 stage binary counters for which the count cycle length is a divide by 5, a divide by 6, or divide by 8. So these guys are a little strange. So if I feed a divide by 2 into a divide by 8, I'm going to get a divide by 16, right? You understand that? If I take a divide by 2 and feed it into a divide by 6, I'm going to get a divide by 12. Now, why do we need a divide by 12? I have no idea. I've never used the 7492 before. You've seen a lot of 7490s and the 7493s. 7490s are BCD counters. 7493s are binary counters. So these guys we have to connect kind of strange, and I'll have to show you that. Because this is the one we'll do the lab on. So if I took a divide by 2 and fed it into a divide by 8, we would get a divide by 16. If I took a divide by 2 and fed it into a divide by 6, then I would get a divide by 12. If I took a divide by 2 and feed it into a divide by 5, I would get a divide by 10, which would be a decade counter, right? You understand? Now, a divide by 2 will always, a divide by a multiple of 2 will always give us a 50% duty cycle. So a divide by 5 is not going to give me a 50% duty cycle. A divide by 6 will not give me a 50% duty cycle on the output, on the final output. All of these counters have gated 0 resets. So here's reset to 0 right here. So I have to use both of these, which is pretty cool because it gives me 2. So a lot of times you can set the modulus of the counter without any external gating because it's got the NAND gate in there for you, a 2-input NAND gate. Now notice on this guy, this gives us 2 resets to 0, and what do you think this guy would be? This is a reset to 9. Now, why you would want to reset a counter to 9, I don't know. Here's my outputs. QA would be the least significant output. QB would be the next one, right? QC, then QD, this would be your most significant output. Here's my counts right here. So I have a count A and I have a what? It's clock, but this is a count. Whatever we want to count, we would bring into this. It's kind of weird. And then of course here, VCC is on pin 6 and my common's on pin 10, which they call what? Ground. And these are the ISO symbols. Thank goodness we don't use those anymore. And this shows me the count on a 7490. So notice it goes from what? 0 through what? 9. And then if we keep counting, it will do what? It would just roll around, right? You understand? And then this is a 74, that's a 7492. This is a 7492. It's going to count from 0 to 11. And like I said, I've never seen this because that's not even a base, right? You understand? By the way, if I needed an octal counter, I could take these guys and set the modulus to 8, right? You understand, which would count from 0 to 7. And there's a 7493. It can count from what? 0 to 15. It's a binary count. And here's the makeup, guys. So you can see this uses internal gating. Like I said, I've never seen a 7492. In fact, I don't think we have one. Okay, guys, I'll take a 2-minute break.